Hello and welcome. You are looking at an overview of quadrilaterals using a bunch of example problems. I believe it's 24 example problems to be very exact with you. Here's what's kind of going to be the breakdown, and not necessarily in this order. Everything's a bit randomized. You're going to see a lot of stuff up at the top. You'll see what I'm talking about. Anyway, our quadrilaterals, the special ones we have, are parallelograms, rectangles, rhombuses, squares, trapezoids, and isosceles trapezoids, and kites. And we will figure out how they place on a set of coordinate axes. So we deal with coordinate geometry using quadrilaterals. And I think that's actually the kicker. We're going to start off there. So jumping straight in here, what we have are two example problems where we will be plotting 4 points, and we will be connecting them. And I'll just start doing it here as I'm talking. And we have to identify what kind of quadrilateral it is. So how do you do that? Thankfully, these will be pretty drawn to scale, which means you could actually probably take a look and say, I think I know what it might be, which is kind of one of the things I will be doing, but you have to be certain of what it is, and it's all math-based. To decide what kind of shape these guys are, specifically what kind of quadrilateral, we will go by the quadrilateral's different properties, and they're listed above on the left, on the top left. Okay. We will determine what something is based on, are lines parallel, are sides congruent to one another, are they perpendicular to one another, etc. So looking at the top, we can decide whether something's a parallelogram just by going by its definition, are opposite sides parallel. Okay, then we can also say, well, if the opposite sides are parallel and if the sides are congruent, then it's a rhombus. Or if opposite sides are parallel and angles are right angles, then it's a rectangle. Or if both of those are true, then it's a square, etc. So we'll be doing both of these examples here, and like I said, these won't look perfect, but I can probably get a good gist of what these might be based on this. Now, how do I know if opposite sides are parallel? In coordinate geometry, what you can do is compare the slopes of one another. If slopes of opposite sides are equal, then they're parallel. And they're perpendicular if slopes of adjacent sides are opposite reciprocals of each other. Distance, we'll be using bit of distance formula. You're actually going to see another slide later that actually shows it. And then we might use midpoint formula at some point. Midpoints can be worked by using the diagonals. By that, I mean if you find the midpoint of both of your diagonals. Let's say I did draw two diagonals before I actually begin this problem. If I drew diagonals here, and I found the midpoints of them, if the midpoint of this has this diagonal going through it, then this diagonal bisects this one. If this diagonal's midpoint has this one going through it, then this diagonal bisects this one as well. So you could use diagonals also with parts of the properties of these shapes, but because they're not listed on here, I won't be using them. Okay, so number 11, I drew the quadrilateral. I have not yet labeled it. Let's do that. N, M, K, L. And then this one here is P, Q, R, S. Okay, anyway. I want to try to find out what shape this is. Now, to me, honestly, it does almost look like a square. And I'm thinking, yeah, it might be a square. It might be, you know what? But though it might be a trapezoid, it might be a rhombus. Who knows, right? But what I'm thinking right now is it could be a square. So some of my tests that I need to do to see if it's a square are opposite sides need to be parallel. Adjacent sides need to be right angles with one another. Okay. And I'd also have to check to see that all the sides are congruent. Now, there are kind of some shorthand ways to do some of this, and what I'm doing right now is I'm drawing what are called slope triangles. They're also drawn as right triangles, but what I'm checking is the rise and run from one point to the next. And what this does actually is two things in one. First of all, I get to find out my rise and run. Second of all, these also work as the legs of a right triangle, and these parts act as the hypotenuse of the right triangle. So I get to find both the slope and distance at the same time, which is pretty nifty. And I'm doing it without actually using the formulas, so to speak. I guess for slope, I am using rise over run, but I'm not subtracting the points from one another. If I drew it, I'm pretty set right now. If I want to find the slope of NM, it's 2 over 4. Up 2 over 4, which reduces to 1/2. The slope of MK is 2 over negative 4, which is negative. I'm sorry, negative 4 over 2, which is negative 2 over 1. The slope of LK, we're rising 2 and running 4, so that's 1/2. And the slope of NL is down 4 over 2, which is also negative 2 over 1. So, what do we got here? 4 slopes. NM and LK are opposite each other. They have the same slope. Therefore, these two sides are parallel. This one and this one. These two guys right here, MK and NL, are opposite each other. They have the same slope, therefore they are parallel as well. At the very least, I know that this shape is a parallelogram. Okay? The next set here, because I'm dealing with slopes, let's look at NM and MK together. Okay, so these guys, they're adjacent sides. If they're opposite reciprocals, which it looks like they are, 1/2 and negative 2 over 1, then these are right angles. So this here is a right angle. Same with MK and LK, negative 2 over 1 to 1/2, opposite reciprocals, boom, boom. And the rest are also right angles as well. They actually kind of have to be, because if this line is parallel to this one and these are right angles, yeah, then that would have to be right angles here as well. So now I know that this is a rectangle. It is a parallelogram, but more specifically, I should be identifying this as a rectangle because all angles are right angles. They're all congruent. Okay? Now, don't just say square immediately. We don't yet know all sides are congruent. What I could do, and I'm just going to do it once, I could go by distance formula or Pythagorean theorem. And if I take one of these, like for NM, if I want to find the length, that would be a squared plus b squared equals c squared, where NM would be your hypotenuse. So 2 squared plus 4 squared. So NM squared is 4 plus 16, which is 20. So the square root of 20 is 2 root 5 units. So NM is 2 root 5 units long, this distance here. Now my question to you is, unless they're asking you to find the side length, was it even necessary for me to do that to determine whether this is congruent to this one? In other words, do I have to find MK by using Pythagorean theorem as well? The answer for you, for me right now, is actually no. And the reason is because I've already drawn these slope triangles. And like I said, these act as right triangles where these are your legs, 2 and 4. These are also 2 and 4. I know this one's negative, but if I square negative 4, I get 16. No matter what, all 4 of these are the exact same right triangle. They're congruent triangles. Therefore, using side angle side right here, side angle side. By CPCTC, all of these sides should also be congruent as well. Not just opposite sides, but all 4 sides together. So these are all congruent. Therefore, this is indeed a square. And again, keep in mind why I said I'm kind of done at that point. I don't need to do any more if I know that these are all congruent to each other by using their slope triangles. That, again, that's exactly why these are pretty good to use instead of plugging things just into a formula. But we can try that later. Okay, number 12. You have your points. Let's do the same thing, because right now I'm looking at this thing and I'm saying parallelogram, right? I don't know for sure, but I want to take a look and decide that. So in order to do that, let's draw some slope triangles again. Some right triangles, essentially. How much are they running and rising or falling or whatever you want to say? Now, someone might ask, does it matter which way I do these? In other words, does it matter whether I do from S to P or P to S? The answer is no, because we're still talking about rise over run, and one of them is going to be considered negative. You just have to make sure that if I'm going from S to P, my run would be negative, my rise would be positive. From P to S, my rise is negative, like it's falling, and my run is positive. So it just depends on which way you do it. So let's calculate all 4 slopes. Well, hang on. Let's do this first. Up 1 over 3. This is over 1, 2, 3, 4, 5, 6, 7, 8. And down 3. This is down 1. And down to the left, 3. Negative 1 over negative 3. See, that's an example of me going this way. So this is to the left. 1, 2, 3, 4, 5, 6, 7, 8, and then up 3. So if I went all this way, notice how those were both negative because I said down and over to the left. Okay, let's go ahead and find some of these slopes here. Slope of PQ is 1 over 3. slope of QR is negative 3 over 8. Okay, down 3 over 8. The slope of RS is negative 1 over negative 3, which does change to 1 over 3. And the slope of SP is 3 over negative 8, which is also negative 3/8. So what we're looking at here are the four slopes. The opposite ones, PQ and RS, are the same. Therefore, these two sides are parallel. And these two also, QR and SP, are the same. Therefore, these are parallel. Now, these are not opposite reciprocals of each other here or here. These would have to be negative 3 over 1 if that was true. So these are not right angles. So we know it's not a rectangle. I figure it's also not a rhombus. I suppose you could always check that. But if one leg is 3 on both of them and the other leg is different, then they couldn't have the same hypotenuse. But if you truly wanted to check, again, you could use Pythagorean theorem and figure out the lengths. Now, that being said, are opposite sides congruent? The answer, besides doing the math, is yes. In a parallelogram, rhombus, rectangle, or square, opposite sides will always be congruent. Not so in a trapezoid or a kite, but that's not what we're looking at here. But how could you also tell? They have the exact same right triangle, 1, 3, negative 1, negative 3, etc. Whatever the answer is, what's the square root of 10, right? These will both be the same because they have the same right triangle. Again, that's the benefit of drawing these first. Anyway, so opposite sides are congruent, but not all sides are congruent. They're not right angles, so it is a parallelogram. This one was a square. And just so you're aware, what if it was not any of these? What if it wasn't any one of these here? What would you call it? You'd call it a quadrilateral because it still has a name. Right. And keep in mind, this thing here, besides being a quadrilateral, it still is a parallelogram. It still is a rectangle. I don't know why I put rectangles. And it's also a rhombus because all sides were congruent. So I could have also called this a rhombus. So it is all three of those, but very most specifically, you are looking at a square. And that's what you want to call it, the most precise name. Most precise name. So although it is the other three, now it is not a kite, it is not a trapezoid, it is not an isosceles trapezoid. Neither is this one here. A trapezoid only has one pair of parallel sides. A kite has no pairs of parallel sides. All right, so there you are. Okay, so let's do a few more where you're trying to find the values of the variables given the shape. This one's an isosceles trapezoid. An isosceles trapezoid has non-parallel sides congruent. These guys right here. The parallel sides are called the bases, and that must be these guys right here, if the other ones were non-parallel. So here's your trapezoid, just like that, and not to say the parallel sides mean anything. In fact, just go by the marks. I don't even think you have to be told this information. What I'm going to do is find out what x is by, again, going by any marks that I know are congruent. In this case, 2x minus 7 and x plus 1. These side lengths, AD and BC, are the same. So I should set these equal to each other. Now, not only are the parallel sides not shown to be congruent, in a trapezoid, they can't be congruent. Otherwise, they are not. Otherwise, it's not a trapezoid. More specifically, it would probably be called, what, a rectangle? Or maybe a parallelogram, I'm sorry. Anyway, solving for x, you're going to get x equals 8. Then you want to find the lengths of all the sides. Well, this one is 8 plus 1, which is 9. That's BC. DC is 8 minus 1, which is 7. This one also must be 9 because this one was 9, but to double check, 16 minus 7 is also 9. And then 8 times 2 is 16, minus 2 is 14. So there are your four side lengths, and we have found everything out there. Okay, this one's a kite, and what happens in the kite is you have two pairs of adjacent sides that are congruent, and then the other side are congruent to each other as well. But none of them, the opposite sides won't be congruent or parallel. So what happens here is I do have an equation right here, and I could set these two equal to each other. The only problem with this equation, of course, is that it has two variables and just one equation, so I couldn't yet solve for one of them. Looks like we have to start on this side first. M plus 3 equals 3m minus 5, which is true. Subtract m, you're going to get 2m equals, adding 5, 8. Therefore, m equals 4. Now that I have what m is, I can substitute 4 in place of m over here and solve for t. So t is going to equal 5 if you subtract 4 on that side. So m is 4, t is 5. Not yet quite done because you still need to find the lengths of all the sides. Make sure you answer the question or questions that are being asked. This is 4 plus 3, which is 7. This should also be 7, 12 minus 5. This is 4 plus 10, 2 times 5, which is 14. Therefore, this should also be 14, 5 plus 9, yes. So like I said, even though you should know what the other one is, maybe you did the math wrong, you should always double check, which I'll do for you. And again, if figures have congruent segments or angles, set them equal to each other to solve for the variables. And that's good. That's it. Okay, now I'm going to specifically look at parallelograms and all of their different properties, not just the definition with opposite sides parallel. What else did I say before? Opposite sides are congruent now in a parallelogram. Same with the angles. Okay? Consecutive angles are supplementary. It's not written down here. I wish I were able to fit that. But that's how we're going to be able to fit some of this other stuff in here. So let's go with number 15. I know this is a parallelogram, so by definition, I should at least put this. Okay? Now, going by other properties, you need to solve for these angles here. What could I do? Without even knowing the other properties, actually, what you could do is say, here are two parallel lines. Here's a transversal that cuts those two parallel lines. Therefore, this angle 1 is a same side interior angle with this angle right here, 79. So I could, without even knowing the opposite angles were congruent, check this out. Measure of angle 1 plus 79 degrees should equal 180. They are supplementary because they are same side interior angles with those parallel lines. Subtract 79, the measure of angle 1 is going to equal 101 degrees. Okay? Now that I know this is 101, guess what? Now I have 1 and 2, or 101, and angle 2 are same side interior angles from these two parallel lines and this transversal. So if I truly didn't know any of the rest of that stuff, I could say the measure of angle 2 plus 101 degrees equals 180. And you subtract 101 and you get back where you started. This equals 79 again. So as you can see, opposite angles are congruent. And I could do the same thing here, but save you time. This is 101 degrees as well. So using the opposite angles are congruent, I was able to figure that out. Or same side interior angles, consecutive angles in a parallelogram are also supplementary. Okay, in this parallelogram right here, as they say, it's a parallelogram, therefore you should do the markings. This one you probably might have to use something with parallel lines and speak on that front. What do I mean by that? Well, you know, actually, no, you don't necessarily have to. I will, though. Okay, so here I have 99 degrees. Got 99 degrees, and number 3 is 1 as well, right here, because these are opposite angles. Therefore, they are congruent. Now, this part right here, I have 38 degrees and 99 degrees. This one right here that's missing, let's just call this X for a moment. This should add up to 180 altogether if I add up all three. So X plus 99 plus 38 equals 180 degrees. 99 plus 38 is 137, I think. Subtracting 137, you'll get X equals, I'm not good with math today, I'm sorry, 43. So this is 43 degrees. Okay, to find out these last two, here's where I said I wanted to probably do a little bit more involving parallel lines. I have two parallel lines here. Forgive the drawing mess. And then I have a transversal. Okay, that gives me alternate interior angles on 38 and 1. Alternate interior angles are congruent. So the measure of angle 1 is 38 degrees. Okay, and then here I have two parallel lines, here and here, cut by the same transversal. And that gives us angles 2 and 43 as alternate interior angles, so they have the same angle measure as well. So measure of angle 2 equals 43 degrees, and as we already wrote down before, measure of angle 3 was 99 degrees. I'm sure you could have gone about it in some order like that properly, but I did angle 3 first. Just go by what you're given and use that. Okay, number 17. Once again, parallelogram, just start with the parallel lines because it really does help when you have alternate interior angles, which I do believe we have here as well, somewhere. For instance, parallel lines here and here, cut by this transversal, gives us alternate interior angles 37 degrees with the measure of angle 1. So the measure of angle 1, is 37 degrees. Okay? And it's good to, if you have the diagram drawn, it's good to just cross that out and put that in there so you can just work on your drawing. Okay, the measure of angle 2 and 3 look like they're going to be the same thing because these are alternate interior angles from the other side, okay, based on these parallel lines. So those are congruent. 63 here, these are vertical angles. These are 63, this is 63 as well. These are not necessarily 63. These are vertical angles with each other. Any of these guys together are linear pairs. This one and this one should add up to 180 degrees. They form a straight angle, so they're supplementary. So 63 degrees plus, let's call this x again, equals 180. Now, why am I doing this? Because I have to fill up an entire triangle to figure out what angle 2 is right here. So x is 117 degrees. So if x is 117, sorry about that, 37 plus 117 plus 2 equals 180. Okay, once again, I'm now within a triangle, and I can figure out the rest. Plus 117, not plus 2, plus the measure of angle 2. 37 plus 117 is 154. I'm sorry, I'll do it up here. Measure of angle 2 plus 154 equals 180. So the measure of angle 2 is 26 degrees. So 2 is 26 degrees. 3 is an alternate interior angle with 2, so that is also 26 degrees. Okay, so there are our 3 angle measures in that, in that parallelogram right there. And there you are. A lot of stuff with parallelograms. We're going to do a few more. Some more parallelograms. This one, you're trying to determine whether the quadrilaterals must be a parallelogram based on what's given. So what we're going to do is determine whether it's enough information to use a property to state that, therefore, at the very least, we are looking at parallelogram. What does that mean? Here I have sets of opposite angles that are congruent here and here. A quadrilateral is a parallelogram if any of the following is true. Both pairs of opposite angles are congruent. Yes, this one is a parallelogram. Okay, both pairs of opposite sides are congruent, just like this one here. Yes, this must be a parallelogram. Vertical angles are congruent. Is that listed on here? I don't think so. I don't think this is necessarily a parallelogram. If you want to be any different with this, I think any two diagonals in a quadrilateral that intersect would always give you vertical angles that are congruent, such as this diagonal, or such as this quadrilateral right here, which apparently I can't connect the points on perfectly. Let me draw a little farther. Yay. This, and I wouldn't call this a trapezoid either. Here's a quadrilateral. These are vertical angles that are congruent. Any quadrilaterals, diagonals, vertical angles should be congruent. This one's a no-go. This one has its diagonals bisecting each other, this one and this one, this one and this one, which is also true, which does make this a parallelogram as well. Now, is it possible for any of these to be a rhombus, a rectangle, a square? Absolutely. Absolutely they could be, because in a rhombus, rectangle, and square, all of these are also true. But this is all about the must. It can be those things. These must be a parallelogram. This just must be a quadrilateral. I don't even know if it has to be any one of these, like I just drew before. So there you go, those four. Okay, one more set of parallelogram stuff. Let's find the variables, and that's it. It doesn't look like we have to solve for any of the lengths. If you want to, you can always plug them in. Let's go by the understanding here that opposite angles are congruent or same side interior angles are supplementary, either or. Looks like, oh, well, no, yeah, actually it looks like we have to go the supplementary route here. So in this parallelogram, opposite sides are parallel, yes? Oh, you know what? Actually, I won't do that. What I was going to do was say add these up, set them equal to 180. Add these up, set them equal to 180. You could. You probably should. But I'm going to practice something a little bit harder for you, where opposite angles are congruent. 4x and 4y plus 4 are the same thing. And then 2x plus 6 and 3y minus 20 are the same thing. Why am I doing this? Because every so often you have to, such as it looks like this one, you're going to have to do the same thing. What am I doing here? Using a system of equations. With only one equation, I could not solve for any set of variables. With both together, it's very possible to do. How so? You can use elimination, you can use substitution, equal values method. I'm actually going to use substitution. What I'm going to do is take this equation and divide everything by 4. I'm going to get x equals y plus 1. Okay? I'm going to take y plus 1 and substitute it in for x in this equation here. And I'll solve for y first. So that becomes 2 times y plus 1 plus 6 equals 3y minus 20. So 2y plus 2 plus 6 equals 3y minus 20. Going on up, sorry about that, 2y plus 8 equals 3y minus 20. Like I said, a lot more work this way. And y equals 28 if I do the proper math. So y equals 28, I still need to solve for x. Let's go ahead and do that. Substitute 28 in for, how about this equation right here? X equals 28 plus 1, that's 29. So there's y and x. And like I said, you could double check. For the sake of time, I won't. But if you double check, make sure the opposite angles end up being congruent. Same with these guys here. Okay, this is once again a parallelogram, at number 23. The diagonals bisect each other, which is probably the way you want to go about this. So this part, 3y minus 3, is equal to 3x. Notice how it looks like I can probably do substitution again. For the sake of practice, I'm going to do a different one. And these two guys equal each other as well. So like I said, let's practice something different here. Let's do elimination this time. Okay, now by elimination, what I'm going to do is line up all variables with one another. I'm very used to looking at them where the x's and y's are on one side of the equation. So what I'm doing here is I subtracted 3y to this side, but I'm bringing the x and y terms over to the left side. And I get 3x minus 3y equals negative 3. And I'm going to move, let's move the 4x over. So this is negative 4x plus 3y equals, and I have to move this 1 over here. So that's going to be negative 2 plus 1, which is negative 1. So items are lined up. When I go down here, I'm going to get 3x minus 4x is negative x. Negative 3y plus 3y is 0. And negative 3 minus negative 1 is, or plus negative 1 minus 1 is negative 4. So x equals 4. Substituting 4 for x, maybe in that top equation, 3y minus 3 equals 3 times 4, which is 12. And you will get y equals 5. So x equals 4, y equals 5, using the understanding that diagonals bisect each other. Therefore, these parts are congruent. The rest after setting these up is algebra. So there's your system. This is the geometry portion. Very algebra after that. Okay, I'm done with parallelograms for a while, or sort of, because a rectangle is a parallelogram. In this quadrilateral, this should just say quadrilateral, in this example right here, with this supposed rectangle, is that what you have is a parallelogram with at least one right angle. Okay? Now that's kind of by definition, that would give you a rectangle, because what would happen is two parallel lines have one line that's perpendicular to at least one of them, so then it's perpendicular to the other as well. Same thing with all of these. I could draw all right angles congruent, or all right angles here. Therefore, this is a rectangle. All right. What does all that mean? In a rectangle, here we're trying to find the angle measures. So we do know this is 90 degrees here and here. How do I want to start you off with this? I'm going to start with angle 1, because 1 and 56 are supplementary here. So the measure of angle 1 plus 56 degrees equals 180 degrees. So the measure of angle 1 is 124 degrees. Okay. Okay, I'm trying to find a different way to tell you what's next for 2 and 3. For starters, I can tell you that these are complementary, meaning they add up to 90 degrees. Okay. But really the next part that I want to mention, and I'm not sure, again, I'm not sure where I should be telling you this in terms of if there's an easier way to tell you, but if the diagonals are congruent, like this diagonal and this one, and this is a parallelogram, so this diagonal bisects this one, and vice versa, they bisect each other, then all of these parts are equal to each other. Boom, 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 boom. Which means nothing more for my case other than right here I have an isosceles triangle. And right here I have an isosceles triangle as well. So in terms of finding 2 and 3, I can go by the idea of isosceles triangle and say that there are base angles that are congruent. Angle 3 and whatever this one is, which I can just call x for now, are the same angle measure. So the measure of angle 3 is x. So right now I'm going to substitute. If I do 56 plus this and it equals 180, I'll just call it x for now. So 56 plus x, which is 2x, equals 180. So I hope you see where I was going with that. And again, I'm trying to think of a different way that should be coming about telling you how to do that without saying isosceles triangles and this and that. But yes, these ones are congruent, these ones are congruent, these ones, and these ones. Anyway, 2x equals 124 again, and we're going to get x equals 62, which is the measure of angle 3. Okay, so these are complementary here, so the measure of angle 2 plus 62 degrees equals 90. Therefore, the measure of angle 2 is 28 degrees. And those are your 3 right there. And you could have done measure of angle 2 in the same way, isosceles triangles, only now this would have been 124. So unless I'm missing something that is just right in my face and I just can't see it, go the isosceles triangle route. That's what you're going to have to do. Okay, number 25 is a rhombus, and all sides here are congruent. Now again, you have to go by the markings. They don't tell you it's a rhombus. You're going to have to figure that out and determine it. Okay. Now in a rhombus, there are some certain things which you could read up here. I'm just going to go by one statement here. The diagonal bisects the angles of a rhombus. And what does that mean? Right here, this angle, 1, is congruent to this angle here, 60. Measure of angle 1 is 60 degrees. Okay. Measure of angle 2 would appear over here as well. So in terms of finding that, we could use vertical angles and say, all right, that's going to be 2. Looks like I can come up with, well, actually, no, I can come up with 2 right now. 2, because it's a rhombus, it's 90 degrees. So 90. Diagonals are perpendicular to each other. You know, every so often, that kind of flies out of my head. Even as a teacher, I can forget at times. I was actually going to tell you another way to find measure of angle 3, which I guess I can still do. If I have here a right triangle, I'm just going to tell you right now, measure of angle 3 has to be 30 degrees, because in a right triangle, the non-right angles are complementary. 60 plus 30 would give you 90 degrees. So that's going to be 30. Here's how I was going to tell you another way to do it. In a rhombus, like I said, these two are congruent to each other, so this entire angle here is 120 degrees, right? Whole thing, 60 plus 60. If that's 120, this whole thing here would have to be 60 degrees, because these are supplementary. If that's 60 degrees and this is bisected, then half of it is 30. So that would also give you 30 there as well for being bisected by this diagonal. So that was going to be the second way to do it. Okay, this last one here, it's the look of a kite. Let's just go ahead and say that right now. Measure of angle 1 is 90 degrees because in all kites, the diagonals are perpendicular. So far, so good. So therefore, this is also 90 degrees right there because they're straight angles and it's a diagonal, or they're perpendicular. Measure of angle 2, here's what I was just talking about before. Measure of angle 2 plus 65 degrees should also give you 90. The non-right angles should be complementary to each other. So the measure of angle 2 is 25 degrees as such. Boom. And there is no measure of angle 3 in this one, so we are done with number 26 and these problems right here. Okay, the next set of problems will involve lengths, and we need to find the length of AC for each of these. Now, each quadrilateral is ABCD, which means AC is the diagonal. Not necessarily a bad thing, but you have to know properties of what you're given in order to make this thing work. Okay, first of all, right here, this shape looks like a parallelogram, and then you have this right angle here, which once again says this is a rectangle. In a rectangle, diagonals are congruent, but they also bisect each other, much like a parallelogram. If they bisect each other and EC is 13, then AE is also 13 inches. AE plus EC should give you all of AC, which is what we're trying to find. No variables this time. Now we're just trying to find the length of what they ask us to find. So 13 plus 13 gives you 26 inches. So the length of that diagonal is 26. And just food for thought, if they were asking us to find dB based on this information, it also would have been 26 because it's a rectangle. Okay, this one too is a rectangle by the right angle symbol. And we're trying to find AC. Okay, so here's an example of trying to find AC based on what I said before. Now in a rectangle, as we also did before, all of these are congruent to each other. So I don't just have to find DE, add them up and say AC is the same. These are all 10. So I should just go ahead and go with that right now. AC is 10 plus 10, which is 20 centimeters. And again, I'm doing it as fast as I kind of need to. If I know it's a rectangle, why do more? Why make it more difficult for yourself? You know what to label. All of these are the same. This one's an isosceles trapezoid. In the trapezoid, one set of opposite sides, the bases are parallel. The other set of opposite sides, the legs, are congruent to each other. In an isosceles trapezoid, the diagonals are congruent. So we're trying to find AC. AC will be equal to dB. dB is dE plus EB, which is 7 plus 12, which is 19 feet. So AC is the same thing as dB because they are congruent to each other. Therefore, AC is 19 feet long. And there you go, based on your properties. If you have any other doubts or whatever, check out all these properties up here. Okay, now what I'm going to jump back into is that coordinate geometry stuff that we were doing before, but now it's a little bit different. Okay, now what we have are generic sets of vertices. You're going to be given most of them, and you have to find maybe one or two missing points. They give you what kind of shape it is, and you go by the properties of that shape to make everything else work. So let me read off some of the top in case so I make sure I know how to say what it is I wanted to say before. We're going to use the properties and definitions of each quadrilateral type to determine what the missing coordinate points are. For example, number 30, in a rectangle, I'm going to use the properties of a rectangle, such as congruent sides or right angles. I'm sorry, not congruent, I'm looking at rhombus. Right angles. That can also tell you some other things, and also we know the parallel, yada yada. So let me start drawing things here. Not all coordinate points necessarily represent the lengths of the sides. What you should always do is relate things in terms of distance from the origin to help you out. In this case, it looks like distance from the origin also will be your lengths. And we're going to use the XY coordinate pairs to determine how far to go. Looks like I didn't finish writing over here. I meant to say how far you should go in that direction. Okay. So I'm sorry about that. And you can use a segment addition postulate to help find the distance between two arbitrarily assigned distances. It looks like that's saved for number 32 there. So I'm going to star that last one for this one right here, so we can talk about that one later. Okay, here I have a rectangle. The distance, this coordinate point here is A0, which as this origin is 0, 0, to go from 0, 0 to A0, it goes A units in the X direction this way. So actually, yes, the length of the rectangle's base here is A units long. Therefore, as this is parallel, or this is on the x-axis, this is parallel to the x-axis, and this is going as a rectangle, this should also be A. Opposite sides in a rectangle are indeed congruent. So this is A units apart from the y-axis, which means your x value will also be A right there. Its height, it goes up to 0b, and this comes from the origin, from the x-axis, so its height is also b, and this is congruent to this one over here, coming from the x-axis, so this height here is also b. The coordinates of p are a, comma b. Number 31, in this square here, the square is rotated 45 degrees one direction, so that now your vertices are actually on the axes. So I wouldn't go by too many assumptions on what something is unless you know all the properties of here. With a square, yeah, you could go by congruent side lengths and stuff, but I'd talk more about the diagonals because these goes vertically and horizontally. The diagonals of a square are not only congruent, but they are also bisecting each other. So all of these have the same length here, 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 and here. So, and also, the next part about this isn't just that, but it's also a question of, is the center of the square, this part, on the origin? If the answer is yes, then you can go in terms of counting how far away these are using these coordinate points. The answer is yes, these are intersecting at the origin here. So this length is going C this way, this is going C this way, this is going C, I guess negative, negative, negative. This one's going C units up in the y direction, where the x value is 0, so it's at 0, C. And that's where P is right there. The third one is, number 32, is extremely difficult in terms of a lot of things that you're going to have to make reference with. For example, here I said, as long as we know this was in the center, we could go C units up. This has no such symmetry or placement where I could say, oh, look, this here, this length from the y-axis to this point in the x direction is negative b units this way. I can't necessarily say it's going b units this way as well. It doesn't look it. I couldn't assume it. There's nothing that says I could do that. But in terms of this stuff, I'm going to be drawing a couple things so you're well aware of where you're at. The C coordinate point right here, the subcoordinate, is referring to the distance from the x-axis up here. It's the y value. So this length here is C if I draw that altitude. This length here is negative a units over in the x direction. Okay, so how should I best reference this? For starters, in a parallelogram, what's actually very interesting, and I can't do too much of this, but if I cut this triangle out of the parallelogram and move it over here, this should fit perfectly in place so that what you can actually make here is a rectangle. See this right here? This ends up being a full rectangle right in green right there, which is true of any parallelogram. If you cut out from the altitude of a vertex down to the other side, the right triangle, and place it over there, you can make a rectangle. What does this have to do with anything? What I'm looking for is this length right here, because I need to find out the x value. I know the y value, by the way. The height's going to be c. I'm well aware of what that should be. This should be c. I don't yet know what this guy is right here. I don't know what this length is. But I do know that this length and this length are the same thing. Okay? Now, if these triangles were congruent here and here, then this length is also the same thing. As you can see, it's pretty confusing. 1, 2, 3 parts there, and a fourth part. What is this length? Well, it's defined in terms of here's negative b, and here's negative a. Negative a, negative b. Negative b is the larger value. It doesn't seem like it because it's shorter, but it is closer to 0, therefore it's the larger value. So I'm going to place it first when I'm finding the distance. I'm going to take negative b and subtract negative a from it, which is negative b plus a, or you could also write that as a minus b. So if you're talking about distance, you could use absolute value of these two things and then subtract a, the larger value, from b. As long as you know which direction you're going, you could flip it and write it from there. So the distance from the y-axis is the length of this part, which is the same as this, and this, which is a minus b. I'm sorry, a minus b, not a comma b. A minus b, comma c. Very difficult example. I hope I spoke through it enough so that you could look at what I was talking about there. There are things with isosceles trapezoids that do the same kind of thing. If I had an isosceles trapezoid, which doesn't look very isosceles, and I cut this out and this out, these are both the same thing. One's reflected. So you could find lengths by using this stuff right here. Now what was I doing with this negative b minus negative a stuff? I was finding the distance between two objects. Say, for example, I had something of length 5 and something of length 8. And I wanted to find the distance between them. I wanted to find out what this is. You know it's 3 because it's 8 minus 5. I was doing the same thing here. I had this length a, or negative a. I had this length negative b. The distance between them is the difference of the two. Okay? So that's kind of where you're going with that. Okay, I have two more problems to do, and they're both proofs. They are not, I'm going to do them as two-column proofs. The reasons will be kind of weird when it comes to talking about them because most of them are just by calculation, mathematical, knowing the formula and stuff like that. So the reasons won't be beautiful, but we're going based on what they kind of tell you and walk through you with the proof with, and they're saying fill in the blanks, make the rest happen. So you're given a square here. I is placed at the origin, and then it goes out a units long, a units tall. As such, as you can see the coordinate points given, we want to prove that the diagonals are perpendicular to each other, FH and GI. So what we're going to do with this is use the coordinate points, find the slopes of FH and GI, and if they're opposite reciprocals of each other, then it's proof that they are perpendicular. So given this, let's find the slope of FH, which is, using slope formula, if you want, or in terms of this stuff, I actually kind of did the slope triangles already. See this right here? Boom, boom. A units over. This would be A units down if I want to think about it like that. But I'm going to use this to help you out in case you want to use it. Y2, I'll use this as x1, y1, and this is x2, y2. So I have y2 minus y1 over x2 minus x1, which once again is negative a over a. Now that is negative 1. We know these values are non-zero values, so any number divided by itself is 1, and you have to take the opposite of it. So this is negative 1 by slope calculation. I'm just going to put that, or slope formula. Okay, we can do this again with g and I. G I'll make x1, y1. I I'll make x2, y2, which are 0, 0, by the way. That's where I is placed at the origin. So this will be x2 minus, where is it? y2 minus y1 over x2 minus x1, which is negative a over negative a, which is positive 1. Let me write this as negative 1 over 1 and positive 1 over 1 because I'm used to kind of slopes working that way. This is by slope formula again. Finally, negative 1 over 1's opposite reciprocal is positive 1 over 1. Therefore, these slopes are perpendicular because they have opposite reciprocal slopes. So it's not much of like a great proof, really. It's kind of, it's kind of weird, just these reasons, but the math is in place. I used what I needed to, this guy, and it made everything all better. So that's for that square. Okay, very last problem, and then we're all done. I have one more proof. I have a rectangle, and I want to know that the diagonals in this rectangle are congruent. So this one, we have a few more things here that are kind of pre-filled out. We're going to fill out the rest here. It's given that the vertex is at the origin. We're going to name B at the place A0. Okay, and D at the place 0B. Now the idea behind this is we have to assign them arbitrary points. However, we do know that B is on the x-axis, therefore its height is 0. D is on the y-axis, therefore its distance from it is 0 in the x direction. And we know that AB and AD are not necessarily congruent. We only know that it's a rectangle, so we can't give them the same letter. So the vertices are on the axes. That's the reason for the zeros. They have different side lengths. That's the reason for these different guys right here. Okay. Now this length this way is A, because in a rectangle you have right angles and opposite sides are parallel and congruent and such and such. You also know that this length from D to C is A, which means C's x value is A. The y value, if this is going up B units, this is also going up B units for that same reason. A, B, A, B. So C has points A, B, like so. Reason, oh boy, what should I speak of? Opposite sides congruent, and parallel for the rectangle. Okay, opposite sides are congruent and parallel, or right angles or something like that. I'm trying to really come up with the best way to speak on that. Again, I'm not sure if you had to list reasons, but getting to this point was important. Okay, AC, what we're trying to find is this length right here. And what's actually really interesting is that this, using Pythagorean theorem or whatever distance formula, stuff like that, this is a squared plus b squared already equals c squared, which is kind of funny. Not that we're calling this thing c squared, we're calling it AC, but AC squared is a squared plus b squared, which is interesting once again because we're using a and b. So let's go ahead and do distance formula though, just to satisfy you guys. If not, use Pythagorean theorem. I mean, straight up you can. I just don't have much room to do this. So what I'm going to do is say the distance of AB is the square root of. So what I'm going to do is A is at 0, 0. C is at AB. I'm going to take these as my x2, y2, and x1, y1. And I'll get the square root of A minus 0 quantity squared plus b minus 0 quantity squared. That's the square root of a squared plus b squared. So I can't really fit it here, but I'll just put a squared plus b squared. So as you can see, you're going to get to the same place as Pythagorean theorem. So to save you time, now that you can trust this formula or trust that Pythagorean theorem works with it, let's do the distance from D to B, or BD now, which also uses A units this way, B units this way. So if BD squared is A squared plus B squared, BD is the square root of A squared plus B squared. Reason I'm using is distance formula, or better yet, Pythagorean theorem. So they use the same distances no matter which way you go about it, but if you assign them these things and you use distance formula, go ahead, you're going to get the same exact thing as you would with Pythagorean theorem. So AC and BD therefore are congruent because equal lengths equals congruent segments. Not very well written. So there's your proofy proof from there. So what we were doing is we had a rectangle. We were proving that the diagonals were congruent using coordinate geometry. Now I know we didn't use midpoint for anything here, but this one's also listed in case you ever need to use it for anything. So that's it. I hope that this was good and decent. And if you ever have any questions, always please ask however need be. It's very important that you understand what it is that you heard. So if you need to rewind anything, please go ahead and do that. It's all on you. Fiend!